Okay, thank you then. So now, the first part, it will be to add some files into this folder. I have here let's see, a few files that I create. So you go here into introduction, HPC, is 13, version control. Here I have project. Okay. So let's do something. I would like to copy all this. Into the location where I am actually working. So I copy all that. So now, basically, I am mimicking the procedure that you will follow manually of creating extra folders and adding some files and start working on a paper. So give a status. It will tell me, okay, now I can see, it will tell you this. I can see a few files and folders that are not part of the version control. They have not version control. So it is not keeping track of them right now. If you want to make them version control, you have to execute git add. And you can do it one by one, or you can put git add to a folder and an entire folder and its contents will be added for tracking. So let's do it one by one. For example, here is git readme, git add, or git status. We'll say, okay, now this is a file that will be committed. That is marked for being tracked. So it's like in a list of promises that the next time that you make a commit, the next time that you execute a commit, you create like a milestone in the system, that file will be considered, will be taken in account. So let's actually make that commitment just with just one file here for you to know. There are several ways of making a commit. If you want to do it this way, it will open your default editor, which in my case is VI. And you can add this, a comment. It's just something that you write for you to know. So the system Git will take care of that, will store that information in a record, in a log that we will see how we can access those logs later. So I am saving this file and it says, okay, I make my first commit. Right now I just have one file, readme. Actually, the content of that file is just a small line with a link to this workshop. That's it. It's a text file. Most of the time, what you want to add into Git are text files. It is able to you can put whatever you want. You can put binary files, figures, images, videos, whatever. But this is especially for just tracking text files. Now, let's see what we did. So now we will add more files here. Some extra ones. Now readme is no longer shown here because the system it knows that the file is the same, has no change since the last commit, but it's still telling me, okay, I have 4 folders here that there are not yet in Git. So git add data, paper, plots, and scripts. Okay. So now I have more files, folders, and all the contents of those folders that were added in this state. And if you want to commit them, we can make our second commit. So we can make a commit. And if you want to avoid opening up an editor and write your text, you can do it right now with the one line message. So adding some folders. Okay. At this moment, Git status says, okay, everything is fine. There is no file that I'm not aware of, version control, and no changes so far. Okay, so now let's edit some of those files. Let's play a little bit with that. Notice this. So let's go and compile this paper. So by the way, this is written in LaTeX, so I will show you a little bit. This is not a workshop in LaTeX by any means. So it's a very, very minimal LaTeX document. What I'm doing here is just some titles and authors, so something very basic, and one figure here. So here I have, so before that, here I have some data. Just this is what I have here: 2 columns, a bunch of numbers. Here I have some scripts that will generate this data, a Python script that will generate the data. And here I have some plots, figure that is generated from that data. So that is like the way that I usually work when I'm writing a paper. So I keep data, let's say not the raw data, but let's say the final table that I will use for the paper, for making some plots or something. I keep it separate, and the scripts, on all the scripts that I use for producing the plots and figures that will go in the paper, and will be there. So part of the as part of the package for the paper. So now here the cluster is not meant for compiling papers. So what I will be doing is using singularity, because I know that there is one singularity. This container, this image includes LaTeX. So I can go here and compile this paper. Okay. So that's what it is. Probably, yeah, you execute it twice, it updated the auxiliary file. And I have the paper. Let's see, let me show you, let me see if I can show you quickly the paper. And I will use this is a good usage for open on demand. So I can go here. Where is the project here? Here is the paper, and this one is the PDF that I just generated. So I can view the nothing special, just a mock of a paper is right here. Okay. So now let's exit from here. Let's see what happened with that. Okay. I can see there is a new file here. There is a track, and there is this file here that was tracked, but those files, we should not be tracking those files because they are files that are not humanly generated, and those files are logs that I'm not interested in. Keep there. So the next step here is to add something for Git to ignore those files entirely. So we will add that. It's editing one file here. It's called git ignore. And add everything that is off. Actually, I would like to remove this one from the Git because this one was included already. So now I'm not getting this one because I ignored it. I need to add this ignore file into the system, so I will add it right now. So now the file will be part of the version control, but I need to remove this one because it was already part of the version. So for that, there is this command git rm, like removing, and I will remove this one. Oh, okay, and I have to force that removal because it was marked. Okay, now yes. So now we need to take a decision what to do with this PDF. Typically, I don't keep track of, in my case, when I'm writing papers, I'm using something like this for papers. I'm not keeping track of the PDF. I always consider that everything that is generated from my sources should be out of my version control. This is how you think when you are writing software. The binaries or the object files are not part of the version control. All that you actually version control are all those files that you create manually, humanly. So I will follow my decision on keeping this file out of the system, and so I will remove it. So now I delete a couple of files that I'm including one, and I will make a new commit. So we will make a comment so you can keep track of that, all those changes. You execute git log, you get all those commits with the message that you add to them. So notice that every single time that I was committing something, I was keeping a track. So you know, and this is the reason why you put the first two lines here, those lines here are for this, to keep in an author, an email on who was changing that, and here is keeping dates, and so it's keeping track of all those changes. So now, the exercise for you, and we will have a bit of time for this. For the exercise is going into this place, and I have here some extra things that you can do. So the scripts here are relatively simple if you are familiar a little bit with Python. They are not extremely, so they are basically the Python version of that. So you can change here, for example, the range would be plotting the figures. You can change that in order to force some changes in the files. So that is something, and adding those files and exploring what you have to do with that. Here I have into the paper, you can just add something. So if you don't know LaTeX, you're not familiar with LaTeX, all that you can do safely will be eventually adding some text here. So you can go and write something here in this section, so you can avoid all that. Just forcing some change in this file. If that is another alternative, is just adding something to this file. So this is just a text file. It's just forcing some changes and making the commits, making the adding and the commits. Those are the three commands that we use: git add, the git status, the git log, sorry, log here, git rm if you want to remove something, and we already did it. So there are a couple of things that are now when we are working on a remote system. So that is so that will be the first exercise. But before that, I will demonstrate this one here. This is another example. So I will go into Github, which is a service over internet that give you access to a centralized repository where several people can commit there. So you can still make commits, make your milestones on your own file if you want. You can have your own Git server, and it's completely separate from this. You can have something like this. There is a version of an environment like this that is called GitLab. So it's a way of having your private web server with all this functionality around. But I'm basically demonstrating the kind of things that you can do when you are interacting with something like it. Let's move on here, and I will git clone. This is one command, git clone this repository. So what is this repository? This is sufficiently small for this purpose. And it's a repository for teaching people about how to do it. It's more for developers. It's more for people who are actually writing code. But it's small, so you can follow the idea how we work with this. So here, what we have some files like this configure AC. Those are files written in a special language for building software. for building software for other professional, for big projects. It's a configure AC. So, and here we have all the source code for this. So a bunch of one C file here, some headers. So this is C code in C, some scripts. So it's a very, very minimal software project. And what we will be doing is exploring the kind of things that we do with this. So notice that I already have some git ignore file. So when I'm ignoring a bunch of things, so when you go and you can add more things to this list. And the reason why I'm adding all those is because this software, it's meant to work like this. And so you execute something that will prepare the software, will create a bunch of files, extra files, a configure. So from this configure file, you generate another configure here. It creates a bunch of scripts or utility scripts. All those are things that are self-generated just by executing. So that for that reason, I am ignoring those files. So this is why you see here git ignore having a lot of those things ignored automatically. So when I execute git status, everything remains clean. I've not done anything yet. So here, when you configure this software, you will execute something like this. It will generate more things here, a make file, things like that. And if I want to compile this software, like what's this software actually? That's right here. So it's something very minimal. It's just one function here that returns the maximum number. Here is the main function that is writing something. This is C code. It's adding some code and executing something. So not much. And you compile this like this. So this is what you execute at the end. So at you end with this executable, but still git status will say everything is clean. I have ignored all those files. So now the exercise that is written here for this is to edit something here in the main C, and you can, if you're not familiar with C, it's here. It's adding one extra line like this, or something like this, and an extra comment. So something that will force the change. So I will add something like this here. By the way, spaces doesn't matter, it's just for style. Print a comment. In C, you always finish with semicolon. And I recompile, will take care of that. Git status. It will tell you that the file have changed, and one file have changed. So if we want to commit that file, I will follow the same procedure. Git add src c. Now git status. The file is now in a stage, and I can commit this one. and I am the owner of the repository, so I can commit that change with a git push. And I don't remember my password, right? So I will have to search for the password and do it, because I make, okay, this is something that remote show origin. This is kind of for advanced command. The way I commit that, I clone the repository was using this line here. So when I'm using this, I need to put my username and password, and I don't have my password here. It's on my personal computer. So that's the difference between cloning the repository like this. Here, I made a mistake of committing this way. The right way of doing it with GitHub is using something like this. You have to install an extra software that is called CLI, the command line interface. They deprecate the access to SSH. Before that, they have the SSH in place. So I have this on my computer, my personal computer, and I can no longer demonstrate that so easily. So if you create an account here on GitHub, and by the way, it's something that I think I comment here. You can have repositories on GitHub, public repositories, as many as you want. But if you want a private repository, you have to pay. Or you, as a member of WU, you can request with us having a private repository. So if you are writing a paper and you want to share it with multiple people, but you still want some privacy, some secret code or paper, if you want that to be exposed around the world, you can request with us a private repository. We can create a repository for you, and you can tell us which will be the people with access to that repository, and we will do that. Let's say it's a good. Some people do it, so I can show you what I can. I can not easily show you also my private computer and the different repositories that other people in WW are working on. So keep in mind that we can use this. We just explored the very minimal of this, very minimal commands for Git, the commands that you use more often. And if you want to explore more in depth, this more than we can do in just 1 hour, there is one entire lesson on Git created by software company. The system from I took all this machinery, and there are also very nice, more in-depth tutorials for Git here. So I just select a few places where I saw some interesting material that will go beyond this very introductory lesson. So please explore those and try to use the materials that I create for you here for forcing some changes here. So it's all right there. Another thing that you can do here on this repository, if you want to work with this, you create your account. It's free with GitHub, and you can go here, take any repository. You can, for example, this one, my repository here, and you can fork it. You can create your own version of it, and that one you can edit. And in that version you can make your own changes and make your own commits. So people fork those repositories from other people so they could work independently on that. So this is another thing that you can do. You can you can have your own version of this code and you can explore those things. And again, if you want to do this for learning how you write auto tools, which is kind of a little bit more advanced thing, feel free to do so. This is for the different workshop, different lesson. So I will give you 15 minutes until 10 a.m. and before we move into the next topic of today. So, any questions, comments? You're welcome. We will continue on topic. Yeah. Okay. So now let's go into compiling codes. Not all of you will compile codes, I know that. But the objective here is more for you to be aware of which are the conditions that make you compile a code in a certain way, why some codes work in some way compared to other. So give you some better understanding of what is inside the code and why you can get parallelization or not. So familiarizing a little bit with the terminology, and so you get a better executions, even if you are never compiling a code. So let's explore. The idea here is to explore a few of the different kinds of codes that you will probably interact for your research, and some of them are related to parallelization. So this one will be the case here for the first one, opening. So if you see that a code mentions something about OpenMP, it's that code is capable of parallelizing using multiple cores on the same machine. So at that moment, you can request more than one core for execution. The way you distinguish those codes that have that capability is because they, for example, in the case of C, they have something like this. So they are using the OpenMP library, and they have pragmas like this. So this kind of symbols here indicate that they have directives for parallelization. The way you compile those codes is like this, and we will see that in a minute with one of the examples that we have here. They are here in so it's this one. So it has this. Big software projects will tell you that they have they are capable of compile with OpenMP. If you can do that, you know, if you can compile those codes enabling OpenMP, you are able to parallelize the execution of it. So let's try with this. Let me see which modules I have here. Well, I already load this one here, which is good. This one, if I compile this code like this, it will fail because it's asking for the OpenMP library. So for compiling this code, I have to actually put this up in this open and execute the code. But this is an small code, an example of code that uses OpenMP. And let me see if I have another one. I have actually several here that uses OpenMP. I think for the exercises. In the case of Intel, I will not. The compilation line is slightly different. So it's Q OpenMP. So each compiler has its own way of compiling. Even more important than this is if you know that some code works in parallel and uses OpenMP, for you as user, you have control during execution or runtime on the number of threads that you want for that execution. by default, it will use as many threads as cores it finds on the machine. I'm running this very small code on the head node. I know that it will run very fast, so I'm using the, and the head node has 24 cores and it has enabled hyper-threading. So for the code, it looks like having 48 cores. And that's what this code is doing. It's launching 48 threads for execution, which could not be the optimum, could not be what you want. So the way you change that is OpenMP num threads. You can control that and request a different number of threads. And that has performance implications for you. If you request 8 cores on Thorn, if you request 8 cores and use just for a job, and you submit a job, the job will actually use 8 cores. But eventually, the program that you are using is not being aware of that, and you will try to use as many cores as the function system. There's the effect of that is that all those 48 or 40 threads will be squished on 4 or 8 cores. So all of them will be sharing time on this on those 8 cores that you will request. So the performance will go down significantly because they have to switch back and forth between all those 40 threads for making the calculation. In some codes, you can declare that on the command line. I know a few bioinformatics codes that you can declare the number of threads. So you will see this in the documentation. I think BLAST is one of them that you can declare the number of threads that you will be using on the command line. So it's basically another way in the code for helping the user to know how many threads you can use for that. That is what I know for those bioinformatics codes. In general, let's say the codes that people use in physics and chemistry, they use both MPI and another kind of parallelization that we will see in a minute, and OpenMP, and that is good, but that is dangerous. Usually, you go for one or another. You disable OpenMP and you keep the code just running on MPI, or you carefully manage the number of threads so they don't go too high. So they usually you just set up 2 or 4 threads maximum, so you get a little extra performance out of the execution, but you don't let the system to go up to the total number of threads that you see on the system. So that is one thing to mention about OpenMP, how you control that. This is probably the most important message for you. If you are using a code that uses that, control the number of threads with this. MPI. So MPI is a different parallelization technique. In this case, you are actually writing, but basically you are writing the code from scratch to support parallelization. So which is hard, but let's say bit codes, this is what they do. For example, for weather modeling, climate modeling, reactors, nuclear reactors, modeling of those, physics, chemistry, all the big codes use MPI. And this is a small example here about that. I think that you have it here. And I will show you how that compiles. So this one here is MPI. So this is a very different way of parallelizing the code. So you see, you distinguish this because they have this message here and a bunch of those in C, something like that, something that starts with MPI. Or the code will tell you that you can enable MPI during compilation. The way you compile something like this, you need more than just the compiler. So the compiler is not enough. You need more than this. And it's right here. Module load parallel and some implementation of MPI. We have several, by the way. We have OpenMPI implementation that we actually will use. This one here is a different implementation. This one is another implementation of MPI. I will just demonstrate this with OpenMPI, very recent version, because it will allow me to show you some of the nuances of this. So you compile this code with a wrapper, with something that is not directly the compiler. This is how you compile a code like this. And also running with this is different. Or something like this. So you will see some messages here. Those are warnings. So those are not error, even if they tell you here the word error. The important message here, this is a warning, is because we are running this with the fabric. We have, this is something particular for OpenMPI. But the actual execution here is this. And this could, I will not demonstrate that, but this is kind of parallelization that could work, that could make a code running on multiple nodes. It could run using all the cores of 10 machines, so a total of 400 cores. And we have like, how many cores we have? Yeah. We have 6,000 cores total in the entire class. So eventually, in principle, you can use all those cores for the simulation. In reality, you can use, typically, some people use 200 cores, 500, 3, 4, probably 400 cores maximum, but no more than that. For execution. As two of you are from bioinformatics, it's relatively rare to find this kind of codes in MPI. So usually the codes in bioinformatics are parallelized with OpenMP or multi-threading. They do multi-threading that more often than doing this. And the constraint there is usually not processing, but memory. So in bioinformatics, when those genomes are really, really huge, they take more memory than processing. So it's a different kind of thing. But it's worth mentioning. But there are some codes in bioinformatics that uses MPI. So it's okay. So, well, here I was using a different compiler, a different version of OpenMPI for this text, but I just demonstrate that with a different. For those who will be compiling codes actually with MPI, there are some nuances here. So when you are using something like OpenMPI or MPICHO, MPICHO, those versions of MPI, they will give you wrappers like this that will use GCC as they call it, the actual compiler. If you are using MPI, Intel, they will give you those, the same, those three, for Intel MPI compiled on top of GCC, or they will give you those three here for Intel MPI on top of the Intel compilers. So the names here are somehow confusing for some. That those are extra ways of compiling codes with MPI from Intel. In the case of the NVIDIA compilers, what they do is that they have their own version of OpenMPI. They give you their own version. So it will work pretty much like this. So, but the wrappers are on top of the NVIDIA compilers. So now, BLAS and LAPACK. For hardcore HPC computing has been large numerical simulations. Let's say the most usual case for those until recently, it was dense linear algebra. Dense linear algebra means dealing with matrices that usually are huge for HPC, and they have a lot of elements in those matrices. So most of the matrix is populated with elements. That is in contrast with what is called the sparse matrices, or sparse linear algebra, where most of the matrix is empty. So most of the matrix is just pure zeros. So the techniques used for sparse linear algebra are completely different. You don't store the entire matrix as a traditional array. You store just the elements that are non-zero, and the manipulation of those entities is quite different from this one. BLAS and LAPACK were created for dense linear algebra. For manipulated BLAS is basic linear algebra operations. Basic means matrix multiplications, matrix vector, all those combination of operations that you can do with matrices. And LAPACK are more advanced routines. For example, for inverting a matrix, for getting the eigenvalues, eigenvectors, decomposing matrix in lower triangle, upper triangle, diagonalizing, all those kind of operations are the kind of things that you see in LAPACK. Now, the traditional implementation of this is the reference LAPACK. We will see that. I think this one is this one. Okay. I think this one example. Okay, but the name here is also something that's been around for more than 40 years. 40, probably close to 40 years. So this is okay. Those routines come back to Fortran 77. So that's why they usually are uppercase, and the names are kind of old-fashioned. This is a double precision general eigenvalue solver. So it's taking a matrix and it's computing this. So this is the description of this. And this one is written in C, and the actual call for the routine is right here. Okay. Yes, so here. And we will not enter in the details of all the routines in lab. We will just see how this compiles. This will fail. It says, I don't know about this library. So this is the typical error that we get. There are several implementations of MPI, of LAPACK and BLAS. The reference usually is not a good answer for this, because there are better libraries that are parallelized. For example, Open BLAS is one of them. MKL is another. Is something that's a product from So if you want MKL is right here. This is the latest version of MKL. This is a version of BLAS and LAPACK. So those linear algebra routines optimized by Intel for Intel processors. So this is what you should be using in case that you want this. Another alternative for this is right here. Open BLAS, this one, something like this. This is what we actually would use. Okay. So now, when you have this loaded, oh no, this one is. Oh, okay. Yeah, I was showing the wrong example. It's this one that uses this library. So I first compile this code here, just extra library, that an extra object that I need to generate, and this is how you compile this code with Open BLAS. And the execution on okay. Compiling with MPI, it's a little bit more convoluted. You need to add more lines here, and in many cases it works. It's a good idea. So module go the Intel compilers and the MPI library. Change this. My mistake. I loaded one. Okay. My mistake. Type MPI. Okay. Oh, yes. Okay, this is another thing. When you compile Fortran, you need always to compile everything with Fortran. And I did the mistake. I previously compiled this. Is init random C. I compiled it before with Fortran. You cannot mix. You can mix with C, but you cannot mix with Fortran. The objects are different, so that's why I'm getting this error. Okay, now it works. In general, the Intel MK works better, and so give you a little bit extra performance. So it's a good choice. Now, HDF5. This is mostly for people in physics, eventually chemistry, and engineering, where you are dealing with large amount of binary data, like numbers for grids, especially for grids, so large matrices, large amount of numbers, just numbers. It's much better if you store those numbers in a binary file. First, it takes less amount of storage for doing that, and it's easier for the computer to load data that is already binary compared with reading data that is in a text format. So when the file is in text format, it's easy for a human to read, but the computer needs to convert all those characters, all those numbers from characters into numbers and store all that data. It takes a while to do that. So there are solutions for that. And HDF5 is one of those solutions. It's standard, so you can you know that this file will be supported for. It will not change. And also it's something that you can exchange between different architectures. So there are good advantages on using something like this. So this code in particular is, again, is a very minimal code. Is just creating what in HDF is called a data frame, data set, sorry. and I think it's populating with some matrix or minimal data, closing the data set, and that's it. It's a minimal code for HDF5, and I will show you how you compile a code like this. I think it's this one. Probably it's this one. It's creating the file. It's adding the dimensions here. Yes, it's not even populating the data. It's just preparing some matrix, and that's it. So you can compile it with GCC. It will fail first. It doesn't know of anything about HDF5, so you need the module load in libs HDF5, and there are a few versions here, so version 12 is okay. 12 GCC 11.1. Okay. This is one way of compiling a code like this. It works, and it generates, I think, this data set. It generates this one. It's a binary file. So if you try to see this file, I hope it will not damage, but just to show you that those are binary, so you see nothing there. Another way it's to see a binary file, it's something like this. So you will see there is nothing that resembles a character or anything like that. And there is a small routine here which I've done that will show you the content of this. So this is what the system actually creates. A data set with 4 times 6 matrix 4 times 6, and it's right now it's just zeros. An alternative to this way of compiling the code, this, they also provide a wrapper HDF5. Give you something like that. This H5 CC. It does the same thing, but now you don't need to put the library. So they have a nice wrapper. They have a wrapper for C, C++, and there is also a library for Fortran. So those are the 3 main languages in scientific computing. So those libraries usually support all those 3 languages by default. Well, this is one way of compiling this code, or this. So this. Now, something else, FFTW. There's one example here. It's another code written in C that uses sparse Fourier transforms. So it's basically converting from one space to another, the space of real functions and the space of the Fourier space where the frequencies of those functions are visible. So in frequency space. So this is what this routine does. It's basically taking a big array, is preparing the conversion here. So in FFTW, you first make a plan, and after you execute that plan, so this is a very minimal execution for FFT. And this is actually C++. Sorry, this is actually C++. So we will compile this. So the GCC compiler will give you this C++ compiler. So it will fail. will tell you that it doesn't know what to do with this. The header is not known. So we need an extra library for this. Module load libs is right here, libs, and there is just one version for different compilers. So we will be using this one. And now it will comply, and now it's able to find the header because now the module has been loaded, but it's not able to compile because it doesn't know where are the libraries, which libraries should be used. For this one, it's LFTW3, and that's how you compile it. You execute it like this, and this code is actually taking an input here and producing this output. Probably, yes, I actually create this Python script. Let me see what it does. It's taking the input and the output and is making a plot of that. So let's execute it. So for Python, we'll be loading this module, load, length, Python, CPython 3, 9, GCC 11. I am doing everything with GCC 11, so no, they're always speaking the right library for this. Module this, executing the Python 3, the plot. Yes, it's making the plot of this. And nice thing I have here. Where I'm doing this worksheet. I was here, here, and I have the input here, so you can see this file. So I just put a few dots here in some places. That is the input. And the output is here. The Fourier transform of those. Okay, so those are the plots. And what else is here? Okay, so I will actually demonstrate this one from the exercise. Yeah. And the idea is for you to basically redo or compile this. The example that is there in the exercise is this one. Example GSL. So this code is in C, normal C. So it's actually doing some of, and again, dense matrix operations, linear algebra, using another library. It's called GSL. And the way you compile this is right here. It's so you compile it. You try to compile it like this. You will fail. You will say, I don't know what to do with this. There are a lot of routines here. GSL something. And for compiling this, it's L, GSL, and before that is L, GSL plus. That means like this, GSL. Things like this. Right. GSL. Now, let me see. Share some more. DSL C++. Okay. So it's given a matrix and it's computing the inverse of that matrix. So this is just a small exploration of many of the kind of things that many people face when they are compiling codes. So you now can explore a little bit this. If you have questions, if you have one code that you face something special, let me know. I consider for adding this later. But in general, those are the most typical code, the most typical libraries. Let's see if I'm missing something. Oh, so maybe, yeah, maybe I should use boost. So my experience, most of those code reduced to the kind of things that I just showed you: HDF, FFTW, plus, and MPI and OpenMP. So I will give you 20 minutes and we go into the last part of this shell scripting. Actually, I would like to start shell scripting, let's say, in 10 minutes. So it will give us more time. There are a lot of things to mention here. So let's say 10 minutes, 10:50, we will start the shell scripting sessions that eventually is far more interesting for, at least for those in bioinformatics. There are a few things that could be interesting for you. So yes, 10 minutes. Okay. Let's start with shell scripting. You have been using, or you will be launching jobs on the cluster, and as soon as you familiarize yourself with jobs and job arrays, for example, we will be generating a lot of data. Typically, simulations produce a lot of text data, big files when you need to search for some data, or you need to automatize certain operations for the jobs. So we will learn here there are 4 commands or utilities and the idea around shell scripting that allow you to get some of your work down faster, more efficiently, and less prone to error. So here, this system, the shell is also, it's not only for these commands, but also give you an entire programming language for manipulating files, executions, text. There are a lot of power hidden behind the shell. The shell is actually a language that you can program, and we will learn the basics of that program. So you will see here some of the examples, scripts that we will see here on this page. So we learn about the echo. So we will review this. So you can put some text here. This is one thing, and also you can put the output of something. And you can use this to get the execution of this command, and the output being inserted as a text, and the text being shown on the script on the screen. And also all those things, you can put them in a file and make with them on a script. So here is one example here. Example. And you can ask the shell to execute this content with this example 1. This is one way of doing it. If you want, if the lines include something very particular from this shell, this particular shell that is called bash, and this is how you do it. So by the way, this is one of the shells that we have. This is just a generic shell or the default shell on the system. I think we have, let me see if I have, we have the core shell, we have the C shell. We will concentrate just on bash, but just for you to know this, yes, we have the C shell. And there is one that is called dash, not dash. Okay, it's not the only one, but most Linux systems use this one. Even Mac, I think the default shell in Mac is bash. I'm not super sure. And this is the default shell of the system. So now, if you want to convert this into a more proper shell script, you will add in what is called a shebang. That will be the example 2. So you can add this in Linux, in Unix. Extensions have, in general, no meaning. Sometimes some programs recognize the extension, but this is not usually the case. So this is really, really not important. What is important is here, adding to this file. So this file, example2, is a file where you put the first line, this, something like this, a sharp, an exclamation mark, and the location of the shell. So we are using, this is the default way of creating a shell script. When you do this, you can still execute it with this, no problem. And the next step, if you want to get rid of this extra command here, you can make this and this script that's executable. Same thing as you create in a program. You can make this like a normal program, adding the executable permission. At this moment, you can execute this code like this. And the same thing is just making this an executable. You notice that because now the file in those systems that colorate those files, we make different colors for those files. The executable files are usually green or blue. So now this is another. So, and a script is something that requires an interpreter for execution. I show you this kind of script. You can replace if you are using. There are some things that are very particular for Bash that are not part of this. So if you want to ensure that the script will work because it's using Bash extensions, you should put like this, the first line. And this was a very popular language. It's still popular in bioinformatics because there are a lot of things written in Perl. So you will see Perl if you are in genomics or bioinformatics in general. This is still widely used there. TCL is another language, and the environment modules, those modules that I'm loading all the time are written in this language. We will be learning today about this and this, Z and all. And probably you are familiar with this one, right? So this is how you write Python scripts. You should be using today in 2021, you should be using something like this for explicitly asking for the Python 3 interpreter. So let's learn a few things about shell scripting before we move into some exercise. Comments. All comments start with this. You can put several statements and separate those with this, with a semicolon. For more commands in one line. So for example, you can put something like this. So host name will return something like this. Day will return something like this, and calendar will return something like this. So you can put all those in a single line with semicolons. Extra lines. So we have here some example. So you can make new lines with this escape. Here vertical tabulators with this, backspace with this. So here I have one small example that explores all of those things. So let me see, let me review it here, much bigger. Example 4, this one. So here I am making an echo with multiple lines. And this is another one where I am using this to continue on another line. So they will print just this as a one line. Those are making tabulators after each word. So making some spaces. Those spaces are, by the way, not standard. So It could be 6, it could be 8, I think. And those are vertical tabulators here. So there is one example making those. And a new line here. So this is one example. So let's see what happens when we execute this script. It's not yet. Okay, I forgot to make it. So. Written in 2 lines, sticking 1 line. So we make this slash. Those are the tabulators. Those are the vertical tabs here to here. So I will make that. And this quotation mark here. And something with a jump here to a new line. So if you go and compare the script with the actual output that it produced, you will see the effects of all those. Okay, in this language, the double quotes and the single quotes are interpreted differently. Both are used for writing strings, but this one, the double quotes, will interpret the variables, will interpret this kind of variables inside, while the single quote will not. And this is example 3. Example 3 is this one. Yes. So if you execute this one, you will see here it interprets the variable like this. In the second case, it's just printing verbatim this. So that is the important difference between the single and double quotes. In other language like Python, it has no difference at all, single and double. So be aware of that. Wildcards. So you see here that I have a bunch of files with examples, and we saw this the first when you start learning about the command line interface, that you can ask for example, everything that start with example. And it will cover all those. Or you can select example and everything with something in the middle and ending with sh. So we'll exclude this one because this one doesn't has not ending in sh, and we'll print all those. So those are wildcards, the start and the interrogation here. Okay, variable substitution. So we saw this again when we learn about environment modules, about environment variables, that we can declare things like this. And we can make an echo about this. Sometimes it's better to encircle this when you are attaching, for example, multiple comments here. So if you are doing this, let's say echo, let's see, asking something like this. If you put something like this, it will not be interpreted that. So that's how you protect the interpretation. So you put curly brackets on inside. Okay, you can make this. I think that I show you this example that you can execute some operations like this, arithmetic operations like this. And the system is only capable of interpreting integers. So if you want to go beyond that, this is not, by the way, this is not a language for making any kind of numerical operation. It's more for manipulating files, for extracting data from files. We will see that in a minute. But not for numerical text. We saw this, I think, the first day about storing the output of the command into a file. We do it this way. This is another way for redirecting both the standard output and the standard error. So in program can write some things on different entities, the standard output and the standard error. This is something usual in Linux systems. This ampersand in front of it will redirect both to the same file. This is another way of making redirections for the standard error somewhere else. This one is for adding content to one file. So I think we saw this in the file. We are doing this. If we are doing multiple of those, we are getting just one line. But if you are using something like this, just attaching more lines at the end. It's appending the content. Okay, the logical operators that we will use here, the examples, this kind of logical operator exists. This one is the and this one is the OR operator. And this is how you make a condition. We have here, let me see if I have this one in example. I don't know, it's not good. Okay. Okay, this one I should have. So let's treat example. Okay, by the way, this indentation is not important. It's just Bing that is making those. Indentations are irrelevant in Bash, by the way. And so this example is asking for two numbers, I think, and is showing, is comparing those numbers. This is how you capture data from the command line. It's very simple. You capture the first element, second element here. And here I am making a conditional comparing the first one and the second one, and returning which one is less than one. You can do those kind of things in one line. So this is one liner, not remember that. Multiple commands can be separated with semicolon. So here I'm making A equal to 6, B equal to 30, and I'm making the comparison. I'm printing this one. For short things, this is something that you can do. You can do this all the time. So if you want, for example, to print the first numbers, you can start, for example, something like this. Well, we will see this in a minute. for one line, you can explore, you can run things. Loops. So we saw one loop there. This one is for the for loop. So you can use this. You can use this inside, for example, for a submission script, because a submission script, except for those first lines that are comments, the PBS, something, those are, this is a script. So you can, for example, do certain evaluation or do some alignment or something for multiple files. So you can run something like this for multiple files and execute the same command one after the other. So this could be useful. What else? This one is kind of the example that I just showed you, one line. It's a counter, and I'm increasing the counter here. So here we have a small exercise. This one. This one is attached to the previous what we saw previously. This one is a code in C. Now we see. I think that I have here. It's for the exercise. This one is this one. This code is reading here from the first argument here, one number, and it's computing a certain number of elements in the series for computing time. So I will just show you how to compile this code again. Probably is already there. Pilot. Say 316. Okay. So I will compile this MPICC. Let's call it MPI. And this code is returning the value of pi with that error, with 10, using 10 elements in the series. So the challenge is to execute this, just changing this value and submitting the job. So you can go up to pretty high. This code runs relatively quickly. So you can see the precision is going up. Precision, the error is going down here as you increase the number of values of this. So this is like a mock of the kind of thing that you would eventually be interested in doing. For example, when you are running a simulation, and that simulation depends on how big is your time step, for example. You want to optimize your time step, for example, in an MD simulation or a computational fluid dynamics simulation. The time step is a critical component for stability purpose, for stability of numerical stability of the code. So you would like to execute multiple times with different values for a few cycles, for a few iterations, to see if the code is still stable or not. So it's something that you can do here. So here the challenge here is to explore this from 1 up to 100. So same executable, different different number of times here, so changing this value. All that you have to do is change this value and execute, putting this in a loop. Now, more interesting that are those two commands. Learn those two commands and you can do a lot of things very efficiently. So I have here one example is this output log. Yes. So let me see this one. Okay, this is one output from one code, produces a lot of things. You can count the lines of this way. So this code has 92,000 lines. This is, many simulations produce this kind of output. Big output where all the information that you actually need is hidden in all those lines. So it's really hard to get an idea of what is in there. So we will be using commands one by one. Let me see if I can split this. Execute and follow this. Okay. Okay, at least I can do something. And so again, this file has more than 90,000 lines. So the first thing that I will do is extract some of the lines that have some interest. So you search for it. So you know that you are looking for something called EDS. So there are many lines with that message. It's actually capturing some energies here. So that's what I'm trying to capture. Grep will return all the lines in that file that contains a certain string, certain text. This is, by the way, far more efficient, for example, than opening this file with Python or something and trying to parse that file with Python. This is basically there are little chances that you can be faster than this code for large files. This is really optimized. So I'm extracting multiple lines. Some of them are the kind of lines that are interested. Some of them are not. So one of those lines have this at the very beginning. I also have timestamp, but those are not the lines that I want. So there are ways for being more precise on this declaration. And I actually want all those that start with something, eventually with some spaces here, but they start with this and excluding those here. So let's start with that. So the way you do that is with this. This is a symbol for grep, and for something beyond grep that is called a regular expression. That it means start the line with this. So this hot here. So I'm making a space here and this. So the meaning of that in regular expression is I'm grepping everywhere where the line starts with timestamp – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – but nothing else. So this one will no longer qualify for the extraction. The number of space could be 0 or more. If I use this one, means at least 1. So this one will work. Okay, this one. I'm extracting all those lines. Now, I would like to extract content that is after those lines. So if you see, code here, let's go here. So this is how you code into step. Oh. Right. So I'm interested in extracting this line that contains a lot of information, energies, all this. So I would like to get this information here. So that's why I'm asking for only this section that starts with time step. And I will capture 13 lines after this, and eventually 1 line before this, just to get this title. That's what I'm doing. So we do this asking after 13 lines, before 1 line, and it is returning all those lines. Now, from there, we can chain operations. So once you are graphing this, we can extract more data. For example, here, I will be extracting this data. This is what I actually want, the total energy. So I'm extracting just this data. Now, what I would like to do is to take all this data, take this number here, summing all the values here, and dividing by the number of values that I put. For doing that, there is a tool, there is actually another programming language that is called awk. So I will just show you that example for this. So it's awk. So you can, let's start with before that. So I will extract, for example, just this element, the third element. This is number 1. This is element number 2. They is separated by spaces here. And this is the element that I will extract. So this is one way of extracting just 1 column. This is actually another way if you are working with something that produces a table that has multiple columns, and you just want to extract 1 particular column for doing something. This is one way of doing it. 1 line. You extract a certain column from a text file, or what I'm doing here is doing some extra manipulation to the file to extract, and after that, extracting the third column. Oh yes, yes, yeah, you are right. And no, I didn't. Thank you, Nate. And actually, you can separate this and this. I think it's this way to declare which is the separator here. So now in that case, the separator will be this. So yeah, thank you. There are ways to declare in a different separator, which is the kind of thing that you will use in case that you are using, for example, a CSV file, which those files are separated by commas. So this is how you separate a file like that. In this case, for example, they don't separate this because this file looks, or this content looks like this. So you can decide what to use as a separator. So yes, so by default, the separation are spaces. So if you think about separating this with the spaces, this one is the third element in this in the list. So now what we will be doing here is adding the elements, the third element. So here, and I will have a variable here that would be increased. And at the end, for example, let me see if I want to print, for example, the sum. And before this, but there is a conditional here, but that one. And the end. Oh, it did. What I'm doing. Oh, I know. Actually, yes. I was using dollar signs as it with variables. So that is the final one. So basically, I'm getting the average of all those energies in one line. Okay. So now, what else we can do with this? There is one example here. I actually changed this to change this. When I show you how good this is for extracting huge amount of data. So this file, and actually recompress it with a different type compared with this one, because this file is big. This file is. So this file, if you want to compress it with so now this doc, you can know the size of this. So this one is 300 megabytes of data. And if you ask for what is inside here, there are a bunch of folders, and in those folders, we have some output from exactly a job array. So we run a job array of a certain simulation, doesn't matter what, 10 different simulations, and each one of those generate big file with more than 500 lines every single. So we are in total dealing with more than 7 million lines that you want to parse. And we will be doing pretty much something similar that we did before for those. So for example, here, yes. So I will be extracting some data. For one particular case, one of those, this is what I'm getting, right? And now, we learned this. We are getting extra lines. So the line that contains this plus 9 lines, we will be extracting data from that. So we are getting this line and the next lines and the next 9 lines there. And from here, we will be extracting one line before that, just the title. I think it's irrelevant. Yes, the title. And we basically proceed with that. By the way, this is a small table of the kind of things that you can do with regular expressions, how you extract several of those. And here, so this one here is extracting the time, and I'm getting, let's go with something like this. So here I'm extracting the lines that contain time, this one, and I am extracting number 4, 1, 2, 3, 4. So this number here, and I extracting, I think, this number. So those are the 2 numbers that I'm capturing. And now I am, for example, would like to extract the values of those 4 columns and put that into a script. So this is the script in Ogg. You can see this. This one is the so this one, okay, now this one is an example with minimal thing. I think it's this one, mean, max, and average. Yes. The same thing that we did before in one line, you can convert those things into scripts for getting some values, extracting something from a text file, and returning, for example, the minimum, maximum, average, which is useful, for example, for this kind of executions where you want to control the average energy of a simulation in chemistry. So this one is, I think, this one is this example. So this one here is how you run it. This one. Yes. It reads this for this file in no time. You put something like this, and it takes time. It takes 1.3 seconds. In a different lesson in Python, I do exactly this, and it takes more than 1 minute for Python to process all the 10 files. It's more than a minute. That with optimization, that adding optimization to the code. So this one is extremely efficient and very handy for this kind of operations. Okay, by the way, there are things that you can do I don't know if I have this one here. This, yes. So in Linux, some of those tools are able to process data directly with compressed data. So here I'm on C. So you don't need to actually uncompress the file. You can, let's say, create a new file for that. It is able to deal with this file directly. So with this command. So there is one exercise for this, is to count with this file, to count the number of lines. We show you there how you made that. You can count the number of lines, the number of columns, get the first line, the last lines, so the head, the tail, and print the number of lines there with awk. So executing something like this. Mimic what we did before for the sum. So getting the sum of the values, the summing of the first two columns, for example. The average, we saw that. So basically redo the same operation for this case. Extracting two columns in particular. So basically it's the same thing for one case. I think that I can just show you. So this is 100 lines, 100,000 lines. So it's not that big, but it's a nice exercise. So for familiarizing yourself with the extraction of data, with awk, with grep, with set. There is just one thing that I forgot, and it could be useful for some. Let me see this output. And yesterday someone asked me about this. So I have imagined that I grab this dot. That's something. And it's replacing words in a file or in a structure. So you can replace. This is the trick for replacement. This is how you replace in one line a certain word with something else. Is set. So this is a nice trick for that, and it's something that we can use, and we used yesterday for one question. So that's it. I will be around for the next 20 minutes. If you have any question about something like this, or you want me to elaborate on a particular case or particular problem, we'll be doing that related to this. Or by basically related to anything that we talk these days. If you have something more particular that you would like to see, you would like to improve the way you are working with the cluster, job arrays, extracting some data from your data, so you can I can enter in your account and give you a hand on some particular problem. So please feel free to use this 20 minutes for that. If not, thank you very much for your attention these 4 days. That's it. Okay, my pleasure, Michelle. Okay, Michelle. What? Okay.